I welcome everyone to this new video in which I explain the chapter Coordination Compounds from CBSE Class 12. I know your time is precious, so without any further ado, let's get into the video. So basically, coordination compounds are those compounds that are formed by coordination bonds. Now there arises another question. What is a coordination bond? A coordinate bond is similar to covalent bond, but here both electrons in the shared pair come from one atom. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. So now a question might arise in you, why should we study these random compounds? Actually, they are not random. Vital components of biological systems, chlorophyll, hemoglobin and vitamin B12 are coordination compounds of magnesium ion and cobalt respectively. Variety of metallurgical processes, industrial catalyst and analytical reagents involve the use of coordination compounds. Coordination compounds also find many applications in electroplating, textile dyeing and medicinal chemistry. Alfred Werner was the first scientist to explain how coordination compounds are arranged. By studying cobalt-ammonia complexes, he discovered that a metal ion has two types of valencies. 1. Primary valency, oxidation state. This decides how many counter ions the metal needs, like Cl-. Second, secondary valency, coordination number. This shows how many ligands are directly attached to the metal ion. Werner showed that in cobalt-3 complexes, the coordination number is always 6, meaning 6 groups NH3 or Cl- remain attached to the metal inside the brackets. The ions outside the brackets behave as normal ions and can be precipitated as AgCl. He also proposed his theory of coordination compound, wherein the main postulates are 1. In coordination compounds, metals show two types of linkages, valencies, primary and secondary. The primary valencies are normally ionizable and are satisfied by negative ions. The secondary valencies are non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valency is equal to the coordination number and is fixed for a metal. The ions or groups bound by the secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination numbers. He further postulated that octahedral, tetrahedral and square planar geometrical shapes are more common in coordination compounds of transition metals. Thus, CONH363+, CONH35Cl2+, and COCl2NH34+ are octahedral entities, while NiCO4 and PtCl42- are tetrahedral and square planar, respectively. Now let's look at the difference between double salt and complex salt. Both double salts as well as complexes are formed by the combination of two or more stable compounds in stoichiometric ratio. However, they differ in the fact that double salts such as carnallite, KCl.MgCl2.6H2O, Mohr salt, FeSO4.NH4 twice SO4.6H2O, potash alum, KAlSO4 twice.12H2O, etc., dissociate into simple ions completely when dissolved in water. However, complex ions such as FeCN64- of K4FeCN6 do not dissociate into Fe2+ and Cn- ions. Now let's see definitions of some important terms pertaining to coordination compounds. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it is called the central atom or ion. These central atoms for ions are also referred to as Lewis acids. The ions or molecules bound to the central atom or ion in the coordination entity are called ligands. These may be simple ions such as Cl-, small molecules such as H2 or NH3, larger molecules such as NH2, CH2, CH2, NH2, or NCH2, CH2, NH2 thrice, or even macromolecules such as proteins. When a ligand is bound to a metal ion through a single donor atom, as with Cl-, H2O or NH3, the ligand is said to be unidentate. When a ligand can bind through two donor atoms as in NH2, CH2, CH2, NH2 or C2O4 2-, the ligand is said to be didentate. And when several donor atoms are present in a single ligand as in NCH2, CH2, NH2 thrice, the ligand is said to be polydentate. When a di or polydentate ligand uses its two or more donor atoms simultaneously to bind a single metal ion, it is said to be chelate ligand. The number of such ligating groups is called the denticity of the ligand. Such complexes called chelate complexes tend to be more stable than similar complexes containing unidentate ligands. Ligand which has two different donor atoms and either of the two ligates in the complex is called ambidentate ligand.
Examples of such ligands are the NO2- and SCN- ions. NO2- ion can coordinate either through nitrogen or through oxygen to a central metal atom or ion. The coordination number Cn is the number of ligand donor atoms directly bonded to the metal ion. For example, in PtCl6 2- and NiNH3 4 2+, the coordination numbers of Pt and Ni are 6 and 4 respectively. The oxidation number of the central atom is the charge it would have if all ligands were removed with their electron pairs. It is shown as a Roman numeral in parenthesis after the coordination entity name. For example, in CuNi4 3-, copper's oxidation number is +1, written as Cu1. The central atom or ion and its attached ligands enclosed in square brackets from the coordination sphere. Ionizable groups outside the brackets are counter ions. For example, in K4 FeCN6, the coordination sphere is FeCN6 4- and K+ is the counter ion. Coordination polyhedron. The spatial arrangement of ligand atoms directly attached to the central atom or ion defines a coordination polyhedron. Common shapes are octahedral, square planar, and tetrahedral. For example, CuNH3 6 3+ is octahedral, NiCO4 is tetrahedral, PtCl4 2- is square planar. Complexes in which a metal is bound to only one kind of donor groups, for example CuNH3 6 3+ are known as homoleptic. Complexes in which a metal is bound to more than one kind of donor groups, for example CuNH3 4Cl2+ are known as heteroleptic.
Nomenclature in coordination chemistry ensures that coordination compounds are named clearly and without confusion, especially when isomers exist. IUPAC rules are used for writing both formulas and names. For formulas of mononuclear complexes with one metal atom, the metal is written first, followed by ligands in alphabetical order. Polydentate and abbreviated ligands are also alphabetically arranged. The whole coordination entity is written in square brackets with no spaces, and its charge is written as a superscript outside if required. Counterions are added after balancing charges. For naming coordination compounds, the cation is named first, then the anion. Ligands are named alphabetically before the metal. Anionic ligands end in O, while names of neutral ligands are usually unchanged. Special names: aqua for H2O, amine for NH3, carbonyl for CO, nitrosyl for NO. Prefixes mono, di, tri are used, but if the ligand name already contains a number, prefixes like bis, tris, and tetrakis are used. The oxidation state of the metal is written in Roman numerals, and if the complex ion is an anion, the metal name ends in 8.
Isomers are coordination compounds that have the same chemical formula but differ in the arrangement of atoms, and because of this change, they show different physical or chemical properties. In coordination chemistry, isomers are mainly classified into stereoisomers and structural isomers. Stereoisomerism occurs when compounds have the same bonding but differ in 3D arrangement. It includes geometrical isomerism, where ligands may be arranged as cis, adjacent, or trans, opposite, such as cis PT-NH3 twice Cl2 and trans PT-NH3 twice Cl2. Stereoisomerism also includes optical isomerism, where mirror image forms cannot be superimposed and rotate plane polarized light differently. A common example is cis COEN3 3+, which shows optical activity while its transform does not. Structural isomerism occurs when the types of bonds are different. One type is linkage isomerism, seen in ambidentate ligands such as NO2-, which combines through nitrogen in CONH3 5 and O2 2+, yellow, or through oxygen in CONH3 5 ONO 2+, red. Coordination isomerism occurs in compounds like CONH3 6, CrCN6, where ligands may exchange to form CrNH3 6, COCN6. Ionization isomerism occurs when a ligand and counterion interchange, such as in CONH3 5 SO4 Br and CONH3 5 Br SO4. Finally, solvate or hydrate isomerism happens when water may act as a ligand or remain outside the coordination sphere, as seen in CrH2O6 Cl3 and CrH2O5 Cl Cl2 H2O. Werner was the first to describe the bonding features in coordination compounds, but his theory could not answer basic questions like, why only certain elements possess the remarkable property of forming coordination compounds? Why the bonds in coordination compounds have directional properties? Why coordination compounds have characteristic magnetic and optical properties? Many approaches have been put forth to explain the nature of bonding in coordination compounds, viz. Valence Bond Theory, VBT, crystal field theory, CFT, ligand field theory, LFT, and molecular orbital theory, MOT. We shall focus our attention on elementary treatment of the application of VBT and CFT to coordination compounds. According to valence bond theory, a metal ion under the influence of ligands can use its available orbitals such as n-1d, ns, n-1d, ns, or np for hybridization to form a set of equivalent hybrid orbitals. These hybrid orbitals determine the geometry of the complex, such as tetrahedral, sp3, square planar, dsp2, or octahedral, sp3d2, or d2sp3, and overlap with ligand orbitals that donate electron pairs. For example, the complex CONH3-6-3+ is octahedral and diamagnetic. Cobalt in this complex is in the +3 oxidation state with a 3d6 configuration and uses inner 3d orbitals for hybridization, d2sp3, making it an inner orbital or low-spin complex. In contrast, COF6-3- is octahedral but paramagnetic because it uses outer 4d orbitals for hybridization, sp3d2, forming an outer orbital or high-spin complex. Similarly, tetrahedral complexes use sp3 hybridization as seen in nickel tetrachloride, which is paramagnetic due to unpaired electrons. However, nickel tetracarbonyl is also tetrahedral but diamagnetic because all electrons are paired. Square planar complexes undergo dsp2 hybridization, such as nickel tetracyanide, which is in the +2 state and forms a low-spin diamagnetic complex because all electrons are paired. It's important to remember that hybrid orbitals are not physical entities, but a theoretical treatment used to explain the bonding and geometry of coordination complexes. Magnetic behavior of coordination compounds is determined by measuring magnetic susceptibility, which reveals the number of unpaired electrons. This helps predict the structure and type of hybridization in complexes. For metal ions with up to 3d electrons, such as Ti3+, D1, V3+, D2, or Cr3+, D3, two vacant d orbitals are available for octahedral D2sp3 hybridization, so their magnetic properties remain similar whether free or complexed. However, for ions with more than 3d electrons, D4, D5, D6 types, electron pairing may be required to create empty d orbitals, leading to two possibilities: low-spin inner orbital or high-spin outer orbital complex.
This difference occurs because strong field ligands like Cn- cause pairing, low spin, while weak field ligands like F- and Cl- do not, high spin. While the VB theory to a larger extent explains the formation, structures, and magnetic behavior of coordination compounds, it suffers from the following shortcomings. It involves a number of assumptions. It does not give quantitative interpretation of magnetic data. It does not explain the color exhibited by coordination compounds. It does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. It does not make exact predictions regarding the tetrahedral and square planar structures of 4 coordinate complexes. It does not distinguish between weak and strong ligands. Crystal field theory explains the bonding and properties of coordination compounds by assuming that the interaction between the metal ion and ligands is purely electrostatic. In this model, ligands are treated as either point charges if they are negative ions or point dipoles if they are neutral molecules, with lone pairs. When these ligands approach the central metal ion, the electrons present in the metal's d orbitals experience repulsion. Because the ligands do not approach all directions equally, this repulsion is not uniform, and as a result, the originally degenerate 5 d orbitals split into different energy levels depending on the geometry of the complex. In an octahedral complex, 6 ligands surround the metal ion along the axes. The energy difference between the Eg and T2G sets is known as the crystal field splitting energy, or delta zero. The value of delta zero depends strongly on the ligand type, and ligands can be arranged in a spectrochemical series from weak to strong field. Electron arrangement in these split orbitals depends on the competition between delta zero and P, that is pairing energy. If delta zero is small, weak field ligand, electrons prefer to remain unpaired and occupy both the levels, forming a high spin complex. If delta zero is large, strong field ligand, electrons pair up in the lower level before moving to the higher one, forming a low spin complex. In tetrahedral complexes, the arrangement is different because ligands approach between the axes. Here the splitting is smaller and the energy order is reversed. The T2 set becomes higher in energy and the E set lower. Due to the small splitting, tetrahedral complexes are almost always high spin. The G subscript is used for the octahedral and square planar complexes, which have center of symmetry. Since tetrahedral complexes lack symmetry, G subscript is not used with energy levels. Transition metal complexes display a wide variety of colors because they absorb specific wavelength of light as it passes through them. The color observed is complementary to the color absorbed. For example, if a complex absorbs green light, it appears red. Crystal field theory explains this phenomenon through DD transitions. In a complex such as TiH2O6 3+, titanium exists as a 3d1 ion, and the ligands create an octahedral field that splits the 5d orbitals into two energy levels, a lower energy T2G and higher energy Eg level. When light of appropriate energy, blue-green range, is absorbed, the electron is excited from the T2G level to the Eg level. Since the absorbed wavelength belongs to the blue-green region, the transmitted and observed color becomes violet. Importantly, in the absence of ligands, no crystal field splitting occurs, so no DD transition is possible, and the substance appears colorless. This explains why anhydrous salts like CuSO4 are white, while their hydrated forms e.g. CuSO4.5H2O are colored. Crystal field theory successfully explains many important features of coordination compounds, including their formation, geometry, color, and magnetic properties. However, the theory is based on the assumption that ligands behave purely as point charges in case of anions or dipoles in case of neutral molecules. Due to this assumption, CFT predicts that anionic ligands should produce the largest crystal field splitting, but experimentally, many anionic ligands appear at the weaker end of the spectrochemical series. This shows that the model does not fully capture the true nature of metal-ligand interactions. Additionally, CFT ignores the covalent character present in many coordination bonds, which becomes especially significant when ligands form strong orbital interactions with the metal. Because of these limitations, more advanced theories such as ligand field theory and molecular orbital theory (MMT) were developed to provide a more complete and accurate description of bonding in coordination compounds. Homolytic metal carbonyls are coordination compounds in which a metal is bonded exclusively to carbon monoxide ligands. Many transition metals form such complexes, and their structures are well defined and geometry dependent. For example, tetracarbonyl nickel is tetrahedral. Pentacarbonyl iron has a trigonal bipyramidal structure, and hexacarbonyl chromium is octahedral. The metal-carbon bond in carbonyl complexes has dual character, both sigma and pi bonding.
First, a sigma bond is formed when the carbon atom of the cobalt ligand donates a lone pair into an empty orbital of the metal. In return, the metal donates electron density from its filled d orbital back into the empty pi bonding orbital of the carbonyl ligand, forming a pi back bond. This mutual reinforcement of electron donation and back donation is called synergic bonding, and it plays a key role in stabilizing metal carbonyl complexes. And that's all for today. And I wish this video helped you. If it was helpful, only then subscribe my YouTube channel. Okay, let's meet in next video, and RJK is signing off.